Okay, let's start what we were doing last time. Uh, we were discussing uniform continuity, right? Let me show you the definition. Okay, a function is called uniformly continuous if for every epsilon positive there is some delta, so that delta close points are mapped to epsilon close to points. Okay, if this holds for every epsilon, and we call the function uniformly continuous. And then we have seen some examples of uniformly continuous functions and functions which are not uniformly continuous. For example, x squared is clearly continuous but not uniformly continuous. We discussed this example. And then we saw what? Another example, I guess sine x, right? Oh, okay, linear functions are uniformly continuous. Okay, I mentioned that on a closed interval, every function is uniformly continuous. Every continuous function is uniformly continuous, but the proof will require compactness argument, so we will postpone that. We have seen sin x, and we have seen finally that any function on a discrete metric space is not only continuous but uniformly continuous. Okay, now what else? We will now consider a different kind of example. I'll introduce a new function which will be uh, useful for some future investigations. Okay, so let A be any subset. Here x D is a metric space. I don't write D, but we should always keep in mind that uh, X is a metric space. And for any X in X, uh, consider the function uh, D. Uh, okay, let me write theta A from X to R defined by uh, theta A X. Okay. Defined by infimum of distances of x to y, y in A. So what does this mean? I have a subset A, okay, some subset, and then for any x in the space, I measure the distances from the points of A to x, and then I take the infimum, okay. So for each point here, I measure this distance in the metric according to the metric given uh, with x, and then I take the infimum. Of course, infimum means what? Kind of the closest, I mean the smallest distance from x to a point of A. In other words, we may think of this as the distance from x to A, right? The distance from uh, A to X. By the way, this infimum exists because all these numbers are positive. Therefore, this set is bounded from below. Hence, its infimum exists, right? All right, now what we know about this function? What can we say about this function? Now, for any okay, xy in x and z in a, we have what? We have distance from, okay, theta a of x. So this is by definition infimum of the distances from okay, x2, let me write not y but w in a. Okay, here y is a dummy variable, so I can use any letter for that. Well, this infimum is clearly less than d xz, because dxz is one of the terms, one of the elements of this set over which we take infimum. Therefore, this element is greater than or equal to the infimum. But this is less than, clearly, what? This is less than dxy plus dyz by the triangle inequality. This is just definition of infimum, and this is triangle inequality, right? This one is the last inequality, is the triangle inequality. Now let's take infimum over uh, uh, okay. Oh, okay. Now from this we get what? So we get this theta ax is less than dxy plus dyz. And if we take infimum over all z, now, right, z is in a. Now, or I can write this. You see, okay, let me write it this way. Theta ax minus dxy, okay, is less than this. And this is true for all z in a, right? Because z was in a. Now, take infimum over z in a, okay? Well, uh, this expression here, the expression on the left, is not, doesn't contain z. So this is a constant number when you are changing z. And they are all less than this. This means that uh, the number on the left hand side is a lower bound for this expression dyz, where z is ranging over a. Therefore, uh, so maybe I should write this. Hence, theta ax minus dxy is a lower bound for which set? For this set. dyz, z is in a. Since it's a lower bound, the infimum is larger than or equal to this. Hence, thus, uh, the infimum of this uh, theta a y, which is the infimum of all these of this set, is less than the lower bound theta ax minus dxy. So we obtained the following: theta a y minus theta a x is less than minus dxy. Wait a minute, I made a mistake, I guess. Okay. Uh, okay. This is a lower bound. Therefore, infimum of this is greater than. Sorry. The infimum is the greatest lower bound, so I have this. I'm sorry. Okay, now. So we get what? Dxy. I take this to this side and uh, theta ay to the other side. So I have obtained this. I'm sorry. Right, we made a mistake. So dxy is greater than uh, theta ax minus theta ay. Yes, right. We have to be careful. This is a lower bound for the set. Therefore, the infimum of this set, which is the greatest of all lower bounds, is at least this much. So infimum is greater than or equal to this expression. Okay. Now this is for any xy, right? For any xy. Now for any xy in x. Now interchange x and y. Interchanging x and y, we get what? Here I get theta ay minus theta ax. Here I interchange x and y, but this is the same as dxy. So we have seen what? Hence, dxy is larger than uh, both this expression and its negative. Since it is greater than both this expression and its negative, this means this expression is larger than or equal to the absolute value of theta ax minus theta ay. Why is that? Because absolute value is either this number or this number, which are both less than this. Therefore, dxy is larger than the absolute value. Do you have any questions so far? Well, this means what? This means uh, it follows that the function theta a from x to r. X is a metric space, R is the metric space with absolute value. Theta x, uh, the function defined is uniformly continuous. Why is that? Well, uh, just take delta to be epsilon. So whenever you give me an epsilon, I choose my delta to be epsilon. So if dxy is less than delta, then this expression is less than delta, which is epsilon. So in the definition of uniform continuity, just take delta to be epsilon. You will see that this function is uniformly continuous. Not only continuous, but uniformly continuous. Okay. Now, some applications of this function. For example, let's consider the following set. The set x in x such that dxa is 0. What is this set? Well, okay, no, I use this notation. The book uses this notation, but I prefer this one. This might be kind of confusing. What is this? The set of points where theta a function becomes 0. Well, this is nothing but the inverse image of 0 under this function, right? And where okay, I should write like this actually. Inverse image of this set where this, of course, singleton is closed in the metric space. Every one element subset is closed actually in any metric space. In particular, this is closed. So this set is the closed inverse image of a closed set, but our function theta is continuous. Actually, it is uniformly continuous. Therefore, this is a closed set. Hence, this is a closed set. Is a closed set containing, of course, A, because if you choose a point from A, right? If you choose a point from A, then theta ax, what is this? This is y in, this is dxy and y in A. But one of these y's is equal to x because x is already in A. So you have in the set dxx. Therefore, theta ax, which is just the infimum of this set, but this set contains 0, and 0 is clearly the smallest element of this real numbers because they are all non-negative. Therefore, this is 0. So A is mapped to 0 in this set, in this under this function. Therefore, A is contained in the inverse image of theta A. So this set is a closed set containing A, and this implies hence A closure is contained in this set, right? In other words, points in the closure have distance 0 to A, right? This is the set A. Maybe at some boundary points, boundary points may not equal to A. What are the points with 0 distance to A? Clearly, the points here have 0 distance to A, but also the points on the boundary, right? Such a point has 0 distance to A because there's a sequence in A which converges to this point. So the distance becomes smaller and smaller. Therefore, the infimum becomes 0. Actually, we have the following. If indeed, if y is in if x, let me say, is not in a closure, this is a closed set, right? Then there is some positive real number so that bxr lies outside of A, right? So if you choose your x like this, okay, outside the closure, remember closure is a closed set, right? Closed set. Therefore, if you take a point outside the closure, which is an open set, right? Open set. I should write here closure, right? Uh, A closure is closed. This is open. So if you take a point in the open set, then there is a ball like this, which lies completely outside x minus a closure. In particular, in particular, uh, for any point y, let me write these points. Okay, y. So whenever you have a point uh, in particular for any y in a, this y clearly is inside a, therefore it cannot be inside this ball, so that the distance from x to y is at least r, okay, because this ball lies outside a, therefore the distance from x to y is at least r. So if you take infimum, hence theta a x is what? This is the infimum of these numbers, right? As y ranges in a, I just take infimum of these numbers, but all these numbers are at least r unit, therefore their infimum will be at least r. So this is the infimum of dxy y in a, but all these numbers are greater than or equal to r, uh, so this is greater than r. Okay, and r is a positive number. R is a positive number. Uh, hence theta ax cannot be 0 if x is in a, if it is not in the closure. So this means what? If a point is in the closure, then the function becomes 0. If it is not in the closure, then the function is not 0. Actually, it is positive. It is positive. Uh, uh, so thus the point where this function is 0 is exactly a closure. Okay. Therefore, a closure is the set of points whose distance to a is 0. Okay. Okay. Do you have any questions so far? So let me summarize. Uh, we defined this function for any subset we just simply take infimum of the distances of points in A to X. So we regard this as the distance function from A to X or X to A, doesn't matter. We showed that this function is uniformly continuous, and then we showed that actually this is a characterization of a closure. We showed that the inverse image of 0, which is a closed set containing A, is actually nothing but the closure of A. Okay. Now, let A and B be closed and disjoint subsets. Okay. And consider the function g from x to r given by this. Gx is equal to this. I measure the distance of the point x to A and then subtract the distance of the point x to B. Okay. So here is my function. Here is, let's say, the subset A and the subset B. So whenever you give me a point x, I measure the distance. This is, of course, a symbolic picture, right? This is the distance to A, and this is the distance to B. I look at the difference between these two real numbers, okay? All right, what can we say about this function? Well, if x is not, first of all, I have this, okay, gx. Now, for any xy in x, we have, let's see, gx minus gy. What is this? This is nothing but, if I write the definition, so this is theta ax minus theta bx, sorry, minus theta ay minus theta by, right? Just from the definition. And I can group these as follows: theta ax minus theta ay plus or minus, okay, minus theta by minus, no, okay, plus, yeah, theta bx, yes, and apply triangle inequality. So theta ax minus theta ay plus theta y minus theta bx. And I know that we proved already, right, here, this expression, no matter what a is, this expression is less than dxy, right? So whenever you have a subset A, this expression is less than dxy, which implies that theta A is uniformly continuous. So here I have two of those such expressions. Now this is less than dxy and this is less than dxy. Okay, by the previous considerations. So this is just 2xy, 2dxy. Well, so this implies what? This function is also uniformly continuous. In particular, uh, g from x to r is uniformly continuous. Just this time, take your delta to be epsilon over 2. So whenever you give me an epsilon, I just let delta to be epsilon over 2. Then whenever x and y are delta close to each other, gx minus gy will be epsilon, will be less than epsilon. Okay. So this function is also uniformly continuous. All right. Now, once this function is uniformly continuous, I can uh, consider the following. You see, if uh, uh, x is in A, which is a closure, right? Because we choose A to be a positive number. Of course, x will not be in B, which is B closure, because A and B, A and B are chosen to be disjoint and closed subsets, disjoint and closed subsets. So if x belongs to A, then it cannot belong to B. Thus, uh, theta A x is 0, but theta B x is positive because x doesn't belong to the closure. Hence, gx, which is the difference of theta ax minus theta bx, is necessarily negative if x belongs to A. Similarly, if x is in B, which is B closure, then x won't be in A, which is A closure, and thus gx, which is theta ax minus theta bx. You see, this time this is a positive number and this is 0, so this will be positive. So you see, this function is positive uh, on A. So gx is positive if and only if, no, if x is in A, and gx is negative if x is in B. So it means what? Thus, now let U to be this gadget, inverse image of G with subset 0 infinite, which is an open set because G is continuous. 0 infinite is an open set. Inverse image of an open set under a continuous function is open. Therefore, this is an open set, which is an open set, containing A. Similarly, V, which is the inverse image of minus infinity 0, is an open set, is an open uh, subset uh, containing similarly V, which is inverse image of minus infinity 0, is an open subset containing B. So we have found what? Finally, we have this. U and V are disjoint because one of them G takes the positive numbers, positive values. On the other one, G takes negative values, right? Since 0 infinite intersection minus infinity 0 has empty intersection. So we have obtained what? Hence, A is in U, B is in V, and UV are disjoint. So what we have shown is the following. Whenever I have two closed and disjoint subsets of A, of X, sorry, I have a subset A, I have another subset B, and what we have found, there is an open set containing A and another open set containing B, and U and V are disjoint. Okay, they are disjoint open sets. Now let me give one example of such A and B. So consider the metric space XD to be R2 with the D2 metric. So D2 is the usual metric, usual distance function on R2. And consider these subsets. A, which is just the x-axis. So this is x comma y's in R2 where y is 0. So this is the x-axis. The x-axis. And B is this. X comma y's in R2 such that x no, okay, y is 1 over x, and okay, yeah, or let me write this way, xy equals 0. No, xy equals 1. All right, well, you see, A is what? A is just, okay, sorry, A is this, the x-axis, and what is B? B is just the parabola, right? X times y equals 1. Sorry. Yes. So this is y. B, sorry. A is clearly closed, right? Uh, but you may wonder how we can actually show that it is closed. You can consider this function. Uh, let f to be this function from R2 to R uh, by this rule xy equals y, okay, which is clearly closed, which is clearly continuous. You can show that this is continuous using epsilon delta. And what is the x-axis? Then the x-axis is this. It is the inverse image of this function. Uh, it is the inverse image of this closed set under the function f, right? Whenever this function takes the value 0, it means you are on the x-axis. And thus A is closed, right? Because it is the inverse image of a singleton. A singleton is always a closed set. Therefore, its inverse image is a closed subset. Similarly, if h is this function, hxy equals x times y, then what is b? B is the inverse image of this singleton, where this function takes the value 1. But, you know, singleton is also a closed set, therefore its inverse image is a again closed subset, which is closed. Why is that? Since h is continuous, this function is continuous. Why is that? Because, you know, the function taking xy to x is continuous. The function taking xy to y is continuous. And this is the product of two continuous functions. Okay, therefore it is continuous. You can, you know, use either epsilon delta argument or sequence arguments. Since h is continuous and this set is closed. So I have two closed subsets, A and B, and they are disjoint, right? A, B, both closed, and clearly they are disjoint. And I am in a metric space, so there should be two subsets which, which what? Separates A and B, right? Because you see, whenever I have two closed subsets in a metric space, if they are disjoint, I should be able to find such open sets which separates A and B. Where are these open sets? In this case, I have to find two open sets which are kind of, you know, disjoint. How can I do this? Well, I can choose those open sets as follows. Consider this function or this, okay. So it kind of goes in the middle of the rate curve and the x-axis till infinity. And here we have something similar which goes in between. Okay, so this will go, of course, till infinity, and this will go till infinity. What are the open sets? Well, uh, U is this open set outside the, so I have, okay, maybe, all right, let me do it this way. Okay, okay. Now U is this set. U is between these blue lines, which is open, and uh, V is outside this. So V is this and U is this set. And U contains A and V contains B. Here, you know, you may take actually this red, no, blue curve as the curve. You see the y coordinate of a point here is 1 over x. So if you choose the y coordinate here as 2 over x, then the blue curve will be under the red curve, right? So in this case, finding the open set U and V may not be that easy, but you know, we know that they exist, and in this case, we actually uh, can write them down. Okay. All right. I think yeah, we are completing 1 hour. Let me stop here.